when studying the cross product, you're going to run into several properties which are going to look very similar to the dot product properties. I can put a link up above there to the dot product properties. Now, the cross product, so I have here several properties. So I guess it's 1, 2, 3, 4, and 5, although I guess the last two are very similar to each other. And what we want to be able to do is, and what I want to be able to show you, is how you can actually show these properties throughout and how you can think about the actual cross product properties. So let's dive into these, so kind of one by one, and then see what they actually mean. And this will be our first one that I'm going to go over. So this particular property, so when you're slowly getting used to the fact of talking about properties, this symbol, first of all, means if and only if, and very often it's written just as IFF, so if and only if. And what this means is that it's telling us that if the left-hand side, so if this is true, then we know that the two, so in this case, the two vectors v1 and v2 are collinear. Now, please recall what collinear means. So what that would mean is that if we would have v1 vector, this would have been equal to some constant m, so that's some scalar m, so some real number m, not 0, and multiplied by v2. So that's what this would mean, that they're collinear. And moreover than that, so that particular collinear, what it could be is that you have one vector in 1, and then the other one is exactly in the same direction, so possibly like this. It doesn't have to be the same size. It could be bigger, it could be smaller, but it's exactly in the same direction. So it's a vector that has the direction, okay, which is the same, or it has the opposite direction. Now, in these two instances, if you're thinking about this, the angle between them, okay, if you map them on top of each other, where the tail was one on top of the other, the angle would have been 0, right? So we would have been having an angle of 0, or if it's in the opposite direction, then the angle would have been 180 degrees. So, for instance, if you wanted to show this property, and what it means is, let's take the right-hand side. So let's assume that they are collinear. So what that means is, if they're collinear, that means that the angle is either 0 or 180. And therefore, for that, this actually is definitely true automatically just by the definition of what a cross product is. So if you recall, the cross product you can also find, which is just the magnitude of your first vector multiplied by the magnitude of the second vector, and then it is multiplied by the sine of the angle between them, and it is, sometimes some normal vector. Now, in our case, we don't need to find this normal vector. It doesn't matter what this would be, because if we know that they're collinear, we know that the angle is 0 or 180, and therefore the sine of 0 or 180 is just going to be 0. So it doesn't matter what this is, if it's multiplied by 0, this whole thing is basically 0 times this vector, and that is nothing else but the 0 vector. And that indeed is what the left-hand side is telling us. So that's one, and this, what I'm showing you here, would have been the direction from the right to the left. And that would have been showing one side. Now, if you want to show the property in full, because it has the if and only if, so it has the arrows in both, to the left and to the right. So what that means now, we also have to assume that this is true. And if this is true, we have to show that the two vectors are collinear, so that there exists some constant such that basically these two vectors are equal to each other, except there's a multiplication by a constant. So that would be proving it in the opposite direction. So this would have meant that we're proving it in this direction. So we're assuming this right here, and we want to show the others. Now, why am I doing this? And, if you're in grade 12 and you're studying the cross product, why would you be interested? Well, because I'm thinking ahead for you. your teachers maybe in high school won't ask you to prove certain properties, although they should, to get you used to, basically for post-secondary, for university, or maybe for college if you're going to be taking some kind of physics or maybe algebra, and you have to show these things and slowly get used to the concept of proving, okay, properties or maybe some statements. So how would I, do this if I know this? Well, this is going to be a little bit of work. Unfortunately, it's kind of annoying. So what I'm going to do is, because of the fact that I don't necessarily know what the angle is, okay, within here, what I want to do is I want to just go back to the definition of the cross product. And that is just by assuming that they're in their Cartesian vector form. Now, I did the introduction to this. Maybe I'll put up a link up above there, right, to the introduction to the cross product. And really, okay, I like to write it out and figure it out in this way, so that I have my I, my J, my K vectors. And then I'm going to put in here, so this is V1, the X component, V1, the Y component, V1, the Z component. And then I have V2 X component, V2 Y component, and then V2 Z component. And now I'm just going to take the cross product from this. So this is going to yield for me a particular vector. So what that vector is, I'm going to find out each of its components. So let me do that in fast forward fashion and just show you, okay, what is going to be the result. So here is the actual vector that we have, so the cross product itself, and we are told, okay, so that it's basically the zero vector. So this is 0, this is 0, and this is 0. Now with that, because I know this, so let me just expand on one of them, and then the other one I'll speed up the process. So notice that what we have is we have V1 Y, so this is V2Z, and this is going to be minus V2Y, V1Z, and this is equal to 0. Now I'm going to just move these terms around, so V2Z, and this is going to bring this over to the other side, so this is going to be V2Y, V1Z, and now notice what happens is I can take V1Y all over V2Y, so that's this, dividing both sides, and then I'm just going to swap, so V1Z all over V2Z. So notice I have a ratio between the Y component and the Z component, and they're equal to each other. Now I'm going to do that from each one, so let me do that in fast forward fashion and you'll see what happens here. So there you have it. So notice that basically they're equivalent to each other. So, if you can see here, for instance, notice V1X, okay, and then V1X over V2X. So notice that they're basically equal to V1Y over V2Y and equal to V1Z over V2Z. So if you, write this in one line, then what we have and what we find that these are all equivalent to each other. So this is going to be V1Y all over V2Y, and then V1Z all over V2Z. So all of these are equal to each other. So what does that tell us? Notice that V1, V1, and V1, so those components are on top, and V2X, V2Y, V2Z are the components at the bottom. So the ratios are all equivalent to each other. So this is nothing else that they're just equal to some constant that I have right there. And that particular constant, what it tells me is that if I would take one vector, okay, and then compare it to another, I'm basically just have a scaled version of one and the other. So this is like saying V1, okay, which is the first vector, is just equal to M V2. So again, it's just a scaling, but this indeed means that they're collinear. So if you assume that the cross product is equal to the zero vector, then you can show, as I did right now, that indeed that they're just scaled versions of each other. They're just basically ratios, okay, ratio of one compared to another. So that is the first property, and the meaning, okay, is just that you have two vectors that are going to be basically collinear. Their dot products are going to be, their cross product is going to be just a zero vector. That's all that you'll have. There's nothing else. Now, the other properties that we have in here, so this was the first property, okay, within here. Here's our second property that we have, which is this one right there. And this one looks very much like basically a copy of the dot product property. So if you take a look at this, you may recall that this was exactly the same thing that has happened in the dot product. When you have an scalar, okay, that is basically multiplying in this case, the cross product inside, that particular scalar can be distributed, but it's not distributed across both of the vectors. Notice that it only will distribute across one vector, okay, or it will distribute for the other vector. Now, these two are equivalent. So once again, we can show this for ourselves just by actually understanding what the cross product does, okay, so within here. So for this, if you go back to the dot product did the same thing, right? It didn't distribute across both, it only distributed across one of them. And what this is saying is that you can take the cross product between two vectors that you have, and you're going to get a vector out. And that particular vector, which is going to be perpendicular to both v1 and v2, and it's going to have a direction. So now it depends, right? You can think about your right-hand rule, right? So one on top of the other, okay? So what's actually happening there? Okay, so either, it's pointing, well, in this case towards me, okay, or it's pointing, the other way, okay, so towards you. So within here, that particular vector of the cross product is going to be just scaled. That's all. And you can do the same thing. It's equivalent to first scaling, for example, the first vector by k, so making it either bigger or smaller, so depending what that k is equal to, or assuming that it's not equal to 0. And in this case, so what we have is that this result is going to scale v1, and then if you cross product within here, it's going to give you the same thing as if you took the cross product first between the two vectors and then scaled your result. And it doesn't matter if you scale the first one or if you scale the second one. So that's what you would actually have in here. Now, in order to show this, you can start right from right here. So you can start from here. So you can take the cross product between v1 and v2. So you can have that right away. Now, I already have it because we've done it right here because I used v1 and v2. So I'm going to borrow this. Okay, so this is my cross product in between them. So that makes my life easier. So let me copy this and then bring it down because I have these two vectors. So let me paste it. And now notice what it's saying is that you have your k, so this k is going to take this result and then scale it. So it's going to now just scale it by k, okay, so within there. Now, we know by the property of vectors that this does distribute across. So it's going to distribute in here, it's going to distribute in here, and it's going to distribute over here. So that's what's going to happen. And now, if you do that, so within there, so notice what will be the case. So if I distribute that k, it's going to distribute fully. And I can write out, so I can write the same thing. I can say k, and this is going to be v1 y, and this is going to be v2z minus, and notice this is going to be k again, because it's being distributed all the way through. So this is going to be v2y, and then v1z. Now, it's going to do the same thing to the other components as well. Now, I'm going to just leave those components for you, right? So you can do that, and you can put the k right in there. But what I wanted you to notice is, and this is where this comes out, So notice that it's going to be scaling my V1 first. And the reason for that is because now what I can do is I can say, okay, well, here it is, right? So this is my V1 in terms of the scaled version right there that I have. Now in here, so this component right here, so this component can be rewritten because these are just now scalars. So I can bring that k, so this is going to be v2y, and I'm going to bring the k, and I'm going to attach it to the v1 component, right? So now what you would have is you would have k, this is v1y, and then v2z. That's my first component right there. And notice that it is attached to the v1 component right there. And this is exactly what we wanted to see from here, because if we took the cross product, that's what would have happened. Now, you would have done the same thing with the second component right here. You can bring the k inside, attach it to the v1 components, and then you can do the same thing and do it right here. And if you would do that, and then, you can basically take this back, okay, and then show that it is indeed that particular cross product between those two. So you can now take the cross product of the right hand side and you will see that they're going to be equal to each other. So that's that property. So notice that the k, which is a scalar, only distributes to one of the vectors. It does not distribute to both. So please don't make this mistake right here, where if you do have a k, so this k is a scalar, and then you have two vectors which are crossed with each other, like so. Please don't distribute across both of these, which is very common, right? Something that we would like to do, but we only can do that when two vectors are added or when two vectors are subtracted. But not so if, for example, there's a cross product or there's a dot product. And I actually did a video on this distribution that it's incorrect in the dot product. I'll put up a link up above there, okay, where this is incorrect in the dot product, and it would be the same thing. It's not correct, meaning the result is not this. You cannot say that this is going to be the cross product between the scaled of both of these, because that's going to show you that that's not true. So that's the second property that you have in here within this particular result. Now here is the next property, okay, that you have. So this one is a lot simpler. And if you've watched the introduction to the cross product that I did, then this shouldn't really surprise us in any way. So I'm going to just copy this, bring it down here for us. So this is that result. Now, you may remember that in the dot product, so if we had this, so within here, so let me paste this back, but instead, okay, I'm going to remove this. It's not the cross product, but it's the dot product. So in the dot product, the result was actually commutative, right? So it didn't matter if you went V1 times V2, times dotted with V2 or V2 dotted with V1. But for the cross product, you have to be careful. This result right here, this just gives you a scalar out. But this result, or this result, it gives you a vector out. And, you can even think about the rule in terms of the right-hand rule. So if we had, for instance, if this is my V1, so let's say this is my V1 and then this is my V2 right here. So if you were doing these, right, and you would take this cross product right here, so V1 to V2, so you notice that this is going to go in this direction. So it's going to go from V1 to V2, which is counterclockwise. And if you go counterclockwise, right, it's going to be going, so in this case, right, so if you use your right-hand rule, okay, it's going to come out of the paper, right? So it's coming out, okay, of the screen, because as you're going from, okay, so from V1, okay, onto V2, and it's coming out, right? So that's counterclockwise. Now, that is the vector that you're looking for. And now notice, if you go V2 crossed with V1, then what you're doing is you're going, V2 and then onto. So you're going to now go in this direction. So from here to here. So that is now in the clockwise direction. So as you're going through in here, so from V2 onto V1, so notice now it's going to go into the paper, right, or into the screen. So that's the opposite, right? So one points out, one points in, and hence that's why you have this negative, all right? So this did not happen in the dot product. They actually were commutative, right? So you can swap them, but this is not the case with the cross product. So please do be careful. So that's another property that we have for the cross product. So if they're switched, then you got to add your negative sign in there, because the direction changes of your normal. So that's what we have there. And then your last set of properties, so these ones right here, let me copy this down, okay, and then bring it, okay, all the way down over here. So these are the last two, although they're very similar to each other. So it does turn out that your cross product does distribute. So it does distribute, but we have to be careful, because if you're going to be distributing these through as you're going by, so notice that this can distribute across, so you have a plus right there, and it will distribute across there, but notice that it is first, right? So that's what we have in there. So it will distribute, but it's going to be the first vector. So what that means is, if you have two vectors that are added together, so you can have a resultant vector out of those, right? Because you can add two vectors together. And then if you're going to cross, okay, with another vector, so that means this vector V3, okay, is somewhere, okay, we don't know, it might be in 3 dimensions. So that particular V3, so now that you cross it, you're going to go from V3 onto the resultant. That's the same thing as actually doing this, that you can take your V3 and cross it with this first, and then add it to this result right here, which is going to be one vector crossed with the other. So notice that it does distribute across here. Now you can take the components if you wanted to and actually provide the result. It's going to take you a little bit of time to try to do that. So you can write down the components of V1, you can write down the components of V2, so that will be easy, the addition of those. And then you can cross it with V3, so that's going to be a little bit painful to be able to see. And then, okay, once you do that, okay, and you find your actual vector, then you can take the right-hand side, which is going to be this side, and now you're going to have to do 2 cross products, this one and this one, and then their components you can add together, and you will see that they're actually equal to each other. Now, I'm going to do that in completely fast-forward fashion, just to show you that the left-hand side equals right-hand side. Now, I'm not going to do the bottom one right here. I can leave that with you. But what I will say is that if you are now crossing, and this, notice that it happens from the back, then the distribution does work. So you can still distribute, but notice that your actual vector, if it's in the back of the bracket, it will stay in the back. So we cannot change these around. So we cannot say that, oh, well, this now all of a sudden also equals to this. Because we know that this is not true from the previous property, from this property right here. So we cannot cross these back and forth. This is not the case with the dot product, right? With the dot product, you can distribute across, and you can swap because it's commutative. The cross product, you cannot do that. All right? So now let me just take this right here. I'm going to take the left-hand side. I'm going to expand it all the way through. And then I'm going to take the right-hand side and expand that. And then we're going to compare, and you're going to see that these two sides are actually equal. I'm going to do that in fast forward fashion. I'll be right back. All right, so it took a little while, but that's because there's numerous components. So I just wanted to show you. So here, okay, what I'm doing is I basically, let me just clean this up. So I'm basically trying to concentrate on here on the left-hand side. And I took that and found the cross product. So I first do the addition. So that was just the addition of vectors. So that was right here. And then I take the cross product with V3, and then here's my result. So my result, so it's 3 components. I separated it by colors. So they're enormous, but that's fine. And then what I did was I took the right-hand side, so I took this, and did the same thing. So I first did the 2 cross products. So that was, so this one right here, so that's the cross product here, and this is what I got. And then I took this, that's the pink, and then that's the cross product, okay, that I got right here. And then I just added them together. So as I added them together, okay, so this is my result. Now, if you take a look, so are they actually equal? Well, they are equal. So here, let me, steal this. This is the first component. So I'm going to just copy this, okay, and then bring it down just so that you can see it side by side. So that's this one and this one, right? So if you take a look at it, notice, so V3Y, V3Y, V1Z plus V2Z, V1Z plus V2Z, minus V3Z, 3Z, okay, and so on. So I basically just simplified it. And the same thing happens with the second component. So here's my second component. So notice negative V3X, okay, so if I go back in here, okay, V3X, okay, V3Z, so this is going to be exactly the same thing as this, right there. Okay, so that's what you would see there. And then your last component, the same thing as well. So I can steal this over, then copy it, and bring it down, and then you can see that they're basically the same. So notice V3X, V3X, okay, V1Y plus V2Y, which is exactly the same thing here, the subtraction, V3Y, V3Y, and then here's my last items. So indeed, okay, that property does hold. Now I wanted to show you some of these, and I know that the video is rather long because of the fact that I'm showing these particular properties, but I think it's good that you get exposed to showing properties and what you need to do in order to show someone that indeed left-hand side equals right-hand side, or if you have, if and only if statements, okay, that you have to go from the left to take the left, show the right, and then take the right and then show the left. I think it's a good skill to have. So those are the full properties, okay, of the cross product. So don't get caught off guard. You're going to have to it's going to be hard for you to memorize all of it, but remember, use your right-hand rule, right, to kind of guide you along on some of those to be able to see, okay, what the results are. All right, so thanks for watching, and we'll see you in a future video. Bye, everybody.